they are nothing but the ratio based distributions. And we can see that the mean of this particular ratio will be equal to mu1 minus mu2. That is mean of the numerator distribution minus mean of the denominator power series distributions. Similarly, variance equal to sigma 1 square minus sigma 2 square. Sigma 1 square is the variance of the numerator power series and sigma 2 square is the variance of the denominator power series distributions. Uh, of course, we have to put some conditions that this sigma square resultant should not be negative. And ratio of two binomial power series distributions we have considered, and it we have proved that it is a proper probability distribution. It gives us a proper probability distribution. Properties. Characteristic function is given by this. Probability generating function is given by this. Moment generating function by this. Where in place of n, we are getting n1 minus n2. And moments mean is given by this. Variance mu3 dash, mu3, mu4 dash, mu4, skewness, kurtosis. And for n1 greater than n2, the distribution is a positively skewed distribution. If q is greater than p and the distribution is leptokurtic. Mode is given by this. This is the derivation of the mode. It has two modes. It is also a bimodal distribution. And special properties like reproductive property, recurrence relation, limiting recurrence relation, limiting form of the distribution is also derived, like the binomial distribution. It's a limiting form. It goes to normal distribution, and this is the graphical representation of this newly derived distribution, ratio based distribution.
Madam, last 2 minutes, madam.
Okay, sir. And we can apply this particular distribution in insurance claims. Policies may be grouped according to geographical area and socio-economic indicators. For the number of policies n and varying probabilities p, number of claims arising from two areas can be described by binomial form. So this is the graph. These are the probabilities. And in area 2, this is in area 1, probabilities and the graph. This is in area 2, probabilities and the graph, distribution and the graph. And this is for area n2 equal to 6 and p 0.48. And just 1 minute, 0.018. And when p increases, the curve is a negatively skewed for fixed n. And when q increases, the distribution is positively skewed for fixed n. When n1 minus n2 tends to infinite, the distribution tends to normal. And a comparison of binomial derived distribution with the generalized power series. So generalized power series, binomial distribution, and its properties. Binomial distribution and its properties. Binomial derived power series distribution in the binomial form, and these are the properties. Similarly, we can derive the ratio of two power series distributions of Poisson, geometric, negative binomial, etc. also. And we can even take the ratio of any two of them. Instead of binomial versus binomial, we can take it even geometric versus Poisson. Even then, we can derive a new probability distribution. So thank you for giving me this opportunity, sir. Thank you, sir.
Thank you very much, ma'am. Thank you very much for your presentation.
Thank you, sir.
The forum is open for any questions or discussions or clarifications to be done with madam. Madam, you said about the insurance industry application.
Yes, sir.
N1 and N2 are two different sectors.
Yes, sir.
So can we go for the sample size? Is I think N1 is 6, N2 is 6. I see
Yes,
that
sir.
very small number. Or
Yes.
we can apply for a larger when we go for reality.
Sir, as I already shown you, the limiting form is also calculated. So for
Okay.
larger case, it goes to normal distribution.
Normal distribution.
Normal distribution. Any other questions, suggestions?
So if there is no more questions, let us thank the speaker, madam,
Thank you
for
so much for giving me the opportunity.
thank you, ma'am. Thank you so much.
Thank you, sir. Thank you.
So we are running out of time. So now
Yes.
we call upon the next speaker, Dr. G. Shirisha,
Thank you.
Assistant Professor in Usman University. Madam is available.
Yes, sir. Namaste, sir.
Namaste, madam. Namaste.
Good afternoon, sir.
Good afternoon. Good afternoon, ma'am. So now we have the second eminent speaker, Dr. G. Shirisha, Usman University. Madam is going to talk about study of mixture distribution with fixed proportion. So Dr. G. Shirisha completed MSc in Upper Statistics in 1995 and PhD in 2009 at Usman University, and started her career as a teaching in statistics from 1993 onwards. But she joined in Usman University in 2014 as a regular faculty. And her research area is various fields, but specifically we focused on reliability theory. And she, to her credit, she has published more number of research articles, the reputed journals in national and international level. And also, she is enthusiastically involved in many academic activities, especially in Board of Studies meeting, research committees, departmental committee, and she involved herself in various affiliated colleges, other colleges near to Usman University. And also, she is a dedicated faculty member in statistics. So such an eminent person who accepted invitation and came over here to deliver her talk in this conference. And she is going to talk about a study on mixture distribution with fixed proportions. So now I call upon Dr. G. Shrisha, madam, to take over the session, and you can take another 20 to 25 minutes for your presentation.
Yes.
Over to you, ma'am.
Hello, sir. There's some problem I have encountered, sir. I'm unable to share the screen. My camera is suddenly stopped working.
Yeah, that is okay, ma'am. The camera is not visible. That is okay. You know how to share? Or should I say?
But when camera is not opening, I'm unable to share the screen as well, sir.
Can you send your slide to me by email?
Your email, sir.
Yeah, or to the conference team. Satish Kumar sir,
Yeah, yeah. Yeah, sir. Okay, I
madam
can
screen is
check.
not visible.
Okay, can I
Okay, okay.
send to Satish sir?
Varun sir.
Okay, okay.
Can I send to Satish sir?
Yes, ma'am. Yes,
Okay,
ma'am.
I'll done.
Please, please share to Satish Kumar sir. So that Shah sir will share the screen.
ఉంది
Yeah, yeah.
మెయిల్లో ఉంది.
మెయిల్లో ఉంది కదా, ఓపెన్ యూ కెన్ ఓపెన్.
మెయిల్ ఓపెన్ చేయొచ్చా? ఇది
Satish Kumar sir, do you assist somebody else to share the
Yeah,
screen?
yeah. Yeah, yeah, yeah. I shall do. I shall do. Okay, okay.
Okay, boss. Okay, boss.
ఈమెయిల్. సార్ జస్ట్ 1 minute సార్.
Yes, ma'am. Kindly send to Satish sir.
చెప్పు జస్ట్ 1
1 minute sir. I'm sending.
ఇందులో ఓపెన్ కదా యాహూ మెయిల్.
అవుతుంది.
ఇందులో ఓపెన్ చేసుకో. ఎక్కడుంది? ఎక్కడుంది? అక్కడ అవసరం లేదమ్మా, ఇక్కడ చెప్పు. ఉంది కదా, ఇది ఇట్లా పెట్టాలా? ఇది ఎట్లా చేయాలి? ఇది మధ్యలో ఇది ఓపెన్ ఉండేటట్టుగా వేరే దానికి వెళ్ళేటట్టుగా
వేరే దీనికి
వాట్సాప్కి వెళ్ళి ఇక్కడ సతీష్ సార్ పంపించింది ఉంటుంది కదా, అందులోకి ఎంటర్ అయిపోయి ఇందులో లింకులు ఉన్నాయి కదా, ఇందులోకి వెళ్ళిపోయి ఇప్పుడు ఇక్కడ యూ హ్యావ్ టు సే ప్రెసెంట్. ఇక్కడ వస్తుంది. మీరు ఎక్కడ ఉంటారు ప్రెసెంట్? షేర్ స్క్రీన్. షేర్ స్క్రీన్. కంటిన్యూ. స్టార్ట్. అక్కడ ఫస్ట్ ఇది మైక్రోఫోన్ మైక్ చేయండి. ఇది ఎక్కడ లేదు, అది అక్కడ లేదు.
So we have not received it.
Is the screen visible, sir?
Yeah, now the screen visible. Can move to the slides.
But it's too small, sir. Too small.
Is it visible, sir, now?
Yes, ma'am. Yes,
Yeah.
Visible?
yes sir. Visible, visible. That's okay. That is okay.
ఓకే.
You can start, madam. You can start.
Yeah.
Good afternoon, everyone, sir. Sorry for the disturbance. I was unable to share my camera on my system. So now I'm using my mobile. Today's my talk is on a study on mixture distributions with fixed proportions. This is my abstract, which says about what Madam has projected just now. We have several probability distributions in statistics, which play a very important role in analyzing in theory as well as applications. And these distributions are used to fit models, real world scenario models in many fields of study. And in these probability distributions are further categorized into many family of distributions. Several statisticians have worked in this side. Today, one among such family is mixture distributions. Mixture distributions, whenever the model or the data has several different exhibits different distributional properties, then we need to use these mixture distributions. And mixture distribution is a convex combination of other several distributions. This is the definition of mixture distributions. Mixture distributions are derived as convex combinations of distributions. If I assume F1, F2, so on, Fk are k different density functions of different distributions defined over the same range of x, then f of x, which is the density of the convex combination of all these distributions, where wi is positive and sum over wi is 1, and these wi's are called mixing coefficients or mixing weights, is also a density function. Whenever these mixing components or mixing weights or these densities are finite, then we will obtain a finite mixture distribution. Today I'm going to project on some of the mixture distributions with fixed proportions. This mixture distributions with fixed proportions study have been started by Gettini et al. In 2008. This statistician has derived, they have derived a new one parameter lifetime distribution known as the Lindley distribution. And this Lindley distribution or Lindley random variable is a convex combination of exponential distribution with scale parameter theta and gamma distribution with this shape parameter 2 and the same scale parameter. And the corresponding mixing weights or mixing proportions taken are theta by theta plus 1 and 1 by theta plus 1. By taking a linear convex combination of these two distributions, the density has been obtained to be as. Hope you are able to see the screen, sir. This is the density which they have derived, the density for a Lindley distribution. And the properties, several properties of this Lindley distribution have been derived to be as mean is theta plus 2 by theta into theta plus 1, and variance is theta square plus 4 theta plus 2 by theta square into theta plus 1 whole square. Similarly, they have derived a characteristic function, cumulant generating function, coefficient of skewness, kurtosis, cumulative distribution function, hazard rate, and mean residual life function by using the standard definitions of these characteristic features. They have got all these, they have derived all these properties. In the same way, the next distribution in this stream is derived by Nano Wong et al. In 2015. They have considered the mixture of two Pareto distributions, and they have obtained the density to be given over here, and their mixing weights they have assumed to be as omega and 1 minus omega. Properties of this distribution are derived to be as mean is beta into alpha square minus 2 alpha plus omega by alpha minus 1 into alpha minus 2. Likewise, variance, moment generating function, coefficient of skewness, kurtosis, cumulative distribution function, hazard rate, all these properties they have obtained. The next distribution is derived by uh, Ramashankar in 2015. Here they have considered a mixture of exponential distribution with parameter theta and gamma with the shape parameter 2, scale parameter theta, but with mixing proportions are different, theta square by theta square plus 1 and 1 by theta square plus 1. Getany et al. Distribution that was also similar, same convex combination, but proportions were different. Fixed proportions are varying over here, and density they have obtained in this way. They have derived the properties to be as mean is theta square plus mean is theta square plus 2 by theta into theta square plus 1. Likewise, they have derived variance generating functions, hazard rate, mean residual life, coefficient of skewness, Curtis's distribution function. Next distribution is also derived by Ramashankar, and here this distribution is named as Akash distribution. It is a two-component mixture distribution. One is exponential with the same parameter theta, scale parameter theta. The other is gamma, but here the shape parameter is taken to be as 3. Scale parameter is the same theta. Mixing weights were theta square by theta square plus 2 and 2 by theta square plus 2. Density they have obtained to be in this form with the corresponding properties, mean, variance, and skewness, Curtis's residue, mean residual lifetime, distribution function, all these they have obtained. In similar lines, we have next distribution by the same person, Ramashankar, introduced, and this distribution is a combination of exponential with parameter theta and gamma with shape parameter 2, scale parameter theta. Third component is also introduced over here. Up till now, we have discussed about two component mixture distributions. This is the three component mixture distribution. Combination of three distributions. One is exponential, the other two are gamma. Gamma first distribution is with parameter 2, the other is with shape parameter 3. And the mixing proportions or fixed proportional weights are theta square by theta square plus 2 theta plus 2 and 2 theta by theta square plus 2 theta plus 2. Last one is 2 by theta square plus 2 theta plus 2 respectively. And this distribution is named as Aradhana distribution. Its density is obtained to be as this expression. Properties have been derived to be mean is theta square plus 4 theta plus 6 by theta into theta square plus 2 theta plus 2. Likewise, all the properties they have derived. Next is also proposed by Ramashankar, which is named as Sujata distribution. This is also a three-component mixture distribution with three-component mixture distribution with scale parameter as exponential three-component. First component is exponential distribution having scale parameter theta. The other is gamma with the shape parameter 2, scale parameter theta. Third one is also gamma with shape parameter 3 and scale parameter theta. And mixing weights are different. We have theta square by theta square plus theta plus 2, theta by theta square plus 2, and 2 by theta square plus theta plus 2 respectively. They have obtained the density to be in this form, and these are the properties of this Sujata distribution. This is the next distribution derived by the same person, named as Amarendra distribution, which is a four-component mixture, exponential gamma, gamma with 3 as shape parameter, gamma with 4 as shape parameter, and the mixing proportions or fixed proportions are taken to be in this form. This is the density which they have obtained, and these are the distributional properties which they have derived. Next distribution is also done proposed by Ramashankar, which is named as Divya distribution. It is a five-component distribution. One is exponential gamma, remaining four are gamma distributions. but with different shape parameters. They are 2, 3, 4, and 5 respectively. These are the following mixing weights, and the density is obtained to be in this form. These are the properties which they have obtained. This is the other distribution derived by the same, proposed by the same person, named as Shambhu distribution, which is a six component mixture distribution: gamma, exponential, and remaining five gamma distributions with different shape parameters. And these are the corresponding fixed proportions. This is the density which they have obtained. These are the properties which they have derived. Hazard rate, mean residual lifetime, distribution function. This is again done by Ramashankar and group. They have introduced one parameter lifetime distribution named as Ishta distribution, which is a two component mixture distribution. One is exponential with parameter theta, the other is gamma with shape parameter 3, scale parameter theta, and the mixing proportions are theta square by theta square plus 2 and 2 by theta square plus 2. This is the density which they have obtained. These are the distributional properties. Again, the same person, Ramashankar, has proposed one more distribution named as Rani distribution, which is again a two-component distribution, but one is exponential with scale parameter theta. The other is gamma distribution with shape parameter as 5. Mixing proportions are theta 5 power 5 by theta power 5 plus 24 and theta power 5 by theta power 5 plus 24 and 24 by theta power 5 plus 24. The density is given to be in this form. These are the distributional properties which they have derived. Then one more distribution. This is the generalization of Sujata distribution, which we have already discussed. This is again a three component mixture. One is exponential, the other two are gamma with shape parameter 2 and 3 respectively. These are the mixing proportions. This is the density which they have obtained. Here in this mixing proportions, they have used one more parameter alpha, and they have generalized this Sujata distribution. These are the properties of Sujata distribution. And the next distribution is proposed by Kamalesh Kumar Shukla. He has named this distribution as Pranav distribution. It is a two-component mixture of exponential with scale parameter theta and gamma with shape parameter 4 and scale parameter theta, with mixing proportions theta power 4 by theta power 4 plus 6 and 6 by theta power 4 plus 6. Density is obtained to be in this form, and these are the distributional properties. The other distribution is also derived by the same person, same statistician, Kamalesh Kumar Shukla, named as Ram Avadh distribution. It is also a two-component mixture, exponential with gamma, but the shape parameter is taken as 6. And the mixing weights have been taken as theta power 6 by theta power 6 plus 120 and 120 by theta power 6 plus 120. This is the density function he has got to be. And these are the distributional properties: mean, variance, moment generating function, skewness, kurtosis, distribution function, hazard rate, mean residual lifetime. Then the other distribution is derived by Kamalesh Kumar Shukla and Rama Shankar. This distribution is called named as Shukla distribution. Here they have considered two components again with the exponential and gamma. In exponential they took scale parameter as theta, and in gamma they took shape parameter as alpha. So they didn't fix the value, they have used variable alpha. And proportions have been taken to be as theta par alpha plus 1 by theta par alpha plus 1 plus gamma of alpha plus 1. They have obtained this density function for Shukla distribution. Mean, variance, and all the remaining properties have been derived for this new distribution. These are the references. And these are the existing fixed proportion mixture distributions. We have been working in the same site, same area of mixture distributions, and we have derived mixture three component mixture distribution of Pareto distributions. Then inverse gamma and inverse Rayleigh mixture distribution we have derived. The Lindley and Lomax mixture we have derived, and inverse gamma three component mixture we have derived. Same similar lines. And this is the table wherein we have consolidated all these distributions, their properties and all. First one is Lindley distribution. What are the components and what is the density? What are the properties? And then we have even explored different additional remarks we have derived. One is this distribution is more flexible than exponential. Then we have obtained the limiting forms of these distributions. Whenever theta by theta plus 1 tends to 1, or theta tends to theta plus 1, or theta is large, linear distribution tends to exponential distribution. And whenever theta is small, linear distribution tends to gamma distribution. So that we can connect this distribution with the applications of gamma and exponential, or a combination of these two distributions. Likewise, the next distribution is a mixture of Pareto distributions. Whenever omega is turning out to be tending to 0, this mixture tends to Pareto distribution. Otherwise, it tends to length biased Pareto distribution. This mixture of Pareto is a combination of Pareto distribution and length biased Pareto distribution. Then the third distribution, I have projected 15 distributions. Third distribution, in the same way we have derived for all the 15 distributions the limiting forms, so that we can compare these mixture distributions with the standard distributions for different parameter values. And we can correlate with the applications as well.
Madam, last 1 minute.
Yes, sir. So these are all the limiting forms of several distributions. Aradhana distribution, limiting form. When theta is small, theta tends to 0, Aradhana distribution tends to gamma distribution. Likewise, when theta is small, Sujata distribution tends to gamma distribution. When theta is small, Amarendra distribution tends to gamma distribution. When theta is small, Divya distribution tends to gamma. Theta is small, Shambhu distribution tends to gamma distribution. In the same way, theta is large, Ishta distribution tends to exponential, and when theta is small, Ishta distribution tends to gamma distribution. Rani distribution, when theta is large, tends to exponential. When theta is small, gamma distribution. Sujata distribution generalization, when theta is small, tends to gamma distribution. And Pranav distribution, when theta is large, tends to exponential. Theta is small, gamma distribution. Ramavad distribution, theta is large, it tends to exponential. Theta is small, Ramavad distribution, it tends to gamma distribution. Then Shukla distribution, when theta is large, exponential. Theta is small, it tends to gamma distribution. So that's how we have studied some more limiting cases of all these discussed distributions. Thank you, sir, for giving me this opportunity. Thank you, sir, for giving me this opportunity to say a.
Thank you, ma'am. Thank you very much for your nice presentation, and you completed on time. On behalf of the organizing committee, I thank the speaker, both the speaker, and also now it's open for discussions or queries by anyone who are, want to get clarification from Shrisha Madam about mixture distribution. I think there is no more questions to be clarified, ma'am. Thank you very much, Dr. Shrisha Madam. Thank you.
Thank you, sir. Thank you. I thank the organizers for giving me this chance.
Yes, ma'am. Thank you. Thank you. So, Professor Satisha, we completed both the talk.
Yeah.
So now it's back to you, sir.
Okay.
Thank you very much for giving the opportunity to share the session. Thank you, sir.
Thank you for the speakers, Professor Jayashree and Dr. Sirisha, for your nice presentation.
Thank you, sir.
Yeah, and also we
Thank you, sir.
thank you. We wish to extend our gratitude to Professor Kaviyaraj for chairing this session and
Thank
supporting
you,
us.
sir.
Thank you so much.
Thank you. Thank you.
Now it is the time to move to the next session. Only 1 minute remains. So let us move to next session. In the next session, we have two speakers, Professor Loganathan sir and Professor Srinivasa, Gede Srinivasa. And,
Professor Satish Kumar sir,
yeah,
good
sir.
afternoon.
Okay,
One
good
small
afternoon.
request,
Yeah,
I am
yeah.
here, I will present my
Okay.
paper. Before that, it seems that Professor Srinivasa Rao has another meeting by 3:30 it seems. So
Oh,
hope that if you permit, please, I request you to permit him to make his presentation first. So
oh,
I will follow that.
oh,
Is
okay.
it all right, sir? Hope that it will not confuse
Okay.
you.
Okay. It's okay.
Thank
Sorry.
you, sir. Thank you. Thank you, Professor Lagnathan.
Thank you. Thank you. I hope Professor Degamar has joined here for chairing the session. Want to check? Okay, he has not joined. I just called him and just let us start. Joined. Okay. Ashwati, Ashwati,
Yes, sir. Yes, sir.
please introduce the chair and briefly introduce the chair and support the chair to run the session, please.
Okay, sir. Good afternoon, everyone. A very warm welcome to all of you to this special invited session of the 10th International Webinar on Recent Trends in Statistical Theory and Applications. We are truly honored to have with us an esteemed chair and two distinguished speakers who bring with them a wealth of knowledge and experience. Let me begin by introducing the chair of this session, Dr. K. Jayagumar. Dr. Jayagumar serves as a professor in the Department of Statistics at the University of Calicut, Kerala, and leads advanced research in time series analysis, distribution theory, and stochastic modeling. He has an impressive publication record with around 90 research papers to his name, covering a diverse range of topics in theoretical and applied statistics. It is a privilege to have him share this session, and we look forward to his valuable leadership and insights. Now, I am pleased to introduce our speakers for the session. First, we have Professor Loganathan A., who is a dedicated academician from the Central University of Tamil Nadu. His work reflects a deep commitment to research, student engagement, and the promotion of academic excellence. Joining him is Dr. Gadde Srinivasa Rao, Professor of Statistics at the University of Dodoma, Tanzania. His work has contributed meaningfully to academic and applied research, and we are fortunate to have him share his insights with us today. Let us now begin this special invited session under the able guidance of our session chair, Dr. K. Jayagumar. Over to you, sir.
Thank you very much. And in this session, our first speaker is Professor Loganathan, and as introduced by Ashwati,
Uh,
he currently works as the professor at the Central University of Tamil Nadu,
Excuse
and
me,
he is
sir. Yeah, there is a change. First speaker is there is some other matters in connection with some other matters. Professor Gede Srinivas now has to be the first speaker, and Logan sir will speak thereafter.
so. As Professor Satish told, our first speaker is Professor Srinivas Rao. He is currently working in Tanzania, as introduced earlier, and he is talking on the topic optimizing clustering of electronic health tabular data. Professor Srinivas Rao, please.
Thank you, Chair. Thank you, Dr. Jaykumar, Chairman of this session. And I would like to thank the organizing committee, specifically Professor Satish Kumar sir, for giving me this opportunity to share my work in this uh, reputed conferences they are conducting every year. Let me open first. So once again, thank the Professor Satish Kumar sir for giving me this opportunity. Am I audible and is it visible?
Yeah. Audible and visible.
Okay. So let me proceed. Today's my topic is optimization of clustering of electronic health tabular data, generative adversarial networks, and Dirichlet process mixed models for an advanced healthcare analytics. So this is an application of the statistics using the artificial neural networks, especially in the public health data. So the outline of the presentation is background and motivation, the research objectives, methodology, key findings, limitations, and finally the future work. So this is the giant work. Actually, this work is uh, my student work. Now he is pursuing the PhD under my supervision, and it is a part of his PhD work. So the context of the problem is synthetic data is widely used in healthcare, but underutilized in cluster analysis. That's why our aim is to study the cluster analysis here. Electronic health records, tabular data, uncover patient pattern, and have a cross domain relevance like finance, fraud, rare diseases, as suggested by these authors. Ensuring the fidelity, utility, and privacy compliance in complex data was studied by this author 2024. Generative model often fail to capture complex statistical dependencies and latent structures, which was studied by the Lee et al. 2023. Lack of rigorous validation frameworks, limited real world adoption in healthcare analytics. This impacts the clustering and predictive modeling performance. Here our aim is to introduce this type of models, that is VAES, that means variance autoencoder. It captures the latent pattern but loose details. It is over smoothing. It was studied by the uh, Magrido et al. 2024. CGANs, that is control data generation adversarial networks. So it control data but suffers from the model collapse. Real INVAP, that is real non-volume preserving transformation. It is poor with categorical and high dimensional data. Another approach is smooth and diffusion model, that is synthetic monitoring oversampling technique and diffusion model, which is limited in preventing the complex correlations or unique high computations. So here we want to introduce GANs generation, high fidelity, preserving data through adversarial training, effective capture complex feature interactions, overperforming VAEs and traditional models, addressing data sparsity, enhancing the synthetic data utility for the task like different clusterings. So objectives of the study is develop a deep learning architecture for synthetic EHR generation, produce high fidelity and privacy preserving synthetic data sets, create robust validation frameworks like fidelity, utility, and privacy, evaluate Dirichlet process mixed models using clustering, and key contributions in this study is novel GAN architecture, realistic privacy compliant EHR data, synthetic data validity using EMD, MMD, JS divergency, and privacy attacks, demonstrate utility through DPMM based clustering analysis, support future healthcare analysis with ethical, scalable synthetic data sets. So this is a data based on the social issue which was collected from the Tanzania. The target population is Tanzanian nations. We have taken a data from EHR database. So among the 9 clusters, 9 zones, we have chosen 3 zones, naming as Matwara, Beya, and Kilimanjaro. We have taken from Matwara 14,555 and Beya from 31,842. From Kilimanjaro zone, we have taken as 52,217 and a total of samples 98,614 patients we have taken, and the data was a secondary data which was collected by the government of Tanzania under the Ministry of Health and NIMR, so and also from local hospitals. So it was conducted in 2018 to 2023. From that data set, we have borrowed this data. So there are some inclusions and exclusions in the data. The inclusions are above 1 year follow-up we considered. Complete demographic and clinical information is also considered. Alive status is considered in this study, whereas we have excluded incomplete data, deceased patients. The research methodology is retrospective cohort study using structural EHRs from the different hospitals. Integration of generative adversarial networks to generate the synthetic data. We have used the GAN method. So here, one is the real data is available, other is we are generating the synthetic data by using GAN's algorithm. So while we are processing the data, we have considered the numerical values, minimum and maximum of normalization. If we get the missing data can be obtained by using either mean median imputation or by using KNN imputation. If the data is less than 10%, we have deleted those data observations. So when the categorical data, we have one hot encoded. What is the GAN structure? So GAN structure is, it is a generator. We use the noise input size is 100, 2 hidden layers like 256 and 128. ReLU, we have used that ReLU also. Batch norming is also used. And what are the discriminator in the GAN structure? We have used 2 hidden layers. Those are 256 and 128. Leak ReLU we have used. L2 regularization also you have used in the synthetic data generation. So what we got the output? The output is sigmoid layer for a binary classification. So we have used 80 out of 20 train test split for evaluation. And what is the GAN methodology? GAN evaluation matrix is for fidelity, KL divergency, MMD, KS test, JS divergency, Wasserstein distance we have calculated. For privacy, membership and attribute inference, differential privacy tests are conducted. For utility, applied for the clustering performance validation. So in clustering approach, DPMM for adaptive non-parametric clustering is used. Used the synthetic EHR with demographic and clinical categorical variables. Bayesian probabilistic assignment using Dirichlet prior and strike breaking process. How we are making the clusters? Cluster quality validation. Internal matrix we used Silhouette index, Dunn index, peak weighted index we have used, whereas for external matrix we have used AMI, Jacquard index, adjusted rank index, Federite ratios we have used for indexing purpose. So as I mentioned, we have taken the 98,641 diabetic patients from these three regions. One is Matwara and other is Beya, third is Kilimanjaro. So here, the features of the data types is mix of categorical, ordinal, nominal, and also continuous variables. The key aspects we have considered is age, gender, body mass index, blood sugar, multimortality status. So, when you are collecting a data, there is a possibility of imbalance. The imbalance issues are tackled by noting down the skewness in age, BMI, blood sugar, and comorbidities. How we are solving the imbalance? By using the GAN's data augmentation, smooth for categorical balancing, whereas if it is a continuous data, we use the log transformation. How we address the data set imbalances? The study evaluate data set imbalance by categorizing the variables into three categories. One is continuous or discrete, second is categorical data, and third is ordinal data. So skewness plots for these categories are presented in the figures 2 and 3, while most of the variables exhibited as a normal distribution, age, BMI, blood sugar level, and the number of comorbidities showed the skewness in synthetic data, resulting in an imbalance ratio of 2 is to 1. To address these imbalances, GANs were used for data augmentation, effectively generating the balance of synthetic samples. Additionally, the synthetic minorities oversampling technique, that is smooth, was applied to enhance the representation of under represented categories variables. For skewed continuous variables, a logarithm transformation was used, as I mentioned previous, and make it to approximate to the normal distribution. These categories ensured that the synthetic data closely matched the target distribution, that is the Dirichlet distribution, and improving the model training and overall performance. So for the skewness of the plots is given in the figure 2, and we'll explain that later. So this figure 2 shows that we have taken the age distribution. This is the first one is age distribution, second is BMI distribution, third is blood sugar level distribution, and fourth is comorbidities. From this, we could observe that in addition to this graphing, we have also considered that box plotting. If you see this box plotting, so especially for the blood sugar and comorbidities, they are required for there are more outliers in these two places. So it affects the model performance, requiring the careful handling through the normalization and resampling technique, especially for these two levels. One is sugar and other is combo-modalities. So for that reason, we have to categorize, we have to uh, imbalancing the data. So to know this categorical data, we have also used the figure 2 for how they are making it to normalities. So this is the figure 2, which illustrates that we have considered the sex, age distribution, and different categories we have taken, and also BMIs we have considered, and education level we have considered here. So different situations we have considered here for different variables. So some of them are nominal, ordinal, and categorical variables. The imbalance in the way in various features is evident, such as high proportion of old age groups, urban residents, low SES, and overweight or obese individuals. So when we are doing the synthetic data generalization for optimization purpose, so these are the challenges we faced. One is mode collapsed in Bayer data, whereas inflating glass in Matwara data, whereas convergence issues in Kilimanjaro data set. So especially when you observe this Bayer data, model collapsed at uh, approach 30. At this place, the model is collapsed and reduced to the output diversity. Whereas Kilimanjaro data displays erratic class pattern, sorry, erratic class pattern, which indicates the convergency challenges for this Kilimanjaro data. To overcome this, we want to make it to stabilization of the data. To stabilize this data, hyperparametric tuning we have used likelihood ratio, we decreased into 0.405. Batch size we have increased to 128. We have updated the ratio, and we have generated the discriminator with 1:5 ratio, and yeah, we have gaming the initialization. So by using this stabilization procedure, we make this data set into like this way. So if you see the now, the loss dynamic of generator and discriminator during the GANs training of the synthetic tabular health data sets. These refinement led to the smooth loss curves, indicating improved generator convergency and well-balanced uh, adversarial training process across all data sets. Previous data set is there is a lot of disturbance. Now they are all both the three regions are in the smooth pattern. So, to another aspect of is evaluation of the synthetic data, fidelity, and similarities. We have considered these aspects for the fidelity, KLD, JS divergency, and Australian and TV distances we have considered. So among these, whatever the lower value shows, that is preferable. So we have calculated for the three regions, and we have considered the different models like VAE, GAN, and real INVP, SMOOT and CGAN, and EHR differences. When we observe these results, in most of the places, GAN outperform than to the other models. And other performance is privacy evolution in synthetic data. Here we, here we have considered different calculations like attribute inference, risk membership, inference risk difference privacy, KNN estimation risk we have used for the both real and simulated data. So again we have compared all the models, and when you observe here, GAN is performing, it shows the lower across all risk types. So the realist, uh, the competent method is real INVP or smooth performance moderately. It is showing well, whereas CGAN and EHR difference shows elevated privacy key. So therefore, from this result, if you are not able to conclude it, instead of that, we may make into the clusters. So that's why we realized that let us use the cluster modeling. So here the cluster model configuration is done by using k-means. Here we have taken k is equal to 4, and Euclidean distance we have considered optimized using the Shilholett score. And for GMM, four components we have used. Gaussian mixed model for probabilistic clustering we have used, and DB scan we have considered the epsilon is zero point 0.5 and minimum sample is 5. Distance based with noise detection is used. And here our aim is to use the DPMM model. So DPMM model is used for non-parametric and dynamic estimation of cluster count. So to know the performance of these methods, we have used SI index and DBI index, ARI index. So the key observations for the model comparison is DPMM dynamics data sets, cluster numbers offering the finger subgroups, provides the probabilistic cluster assignments which reflects the two data heterogeneity, handles the mixed distributions better than the fixed parametric model. So like traditional models, k-mean, GMM, DB-scan rely on the fixed assumptions of limiting flexibilities. So to see the clustering, so this figure shows that the clustering of Matwara dataset, the first span is for the real data sets, whereas the second span is for synthetic data. If you observe both real and synthetic, this synthetic data cluster exhibits tightened grouping, which reduces the intra cluster variability as compared to the real data. Here, intra cluster is it is spreading, so it gives the more intra cluster variability. Whereas here in Matwara, in this data set, the synthetic data, these three are created separately with a distant, and they are very close. So there was a greater intra-cluster distance, making distant groups more visible in synthetic data as compared with the real data. Similarly, we done for the Bayer region also. This is for real data that we consider, that we collected from the records, whereas this is the synthetic data. So here is also the cluster with more uniform shapes, making pattern more interpretable, yield more stable cluster outcomes, reducing the variation. Similarly, for the third region, third region is Kilimanjaro. We have considered the real data set, and this is a synthetic data. Here is also we got the same nature. So therefore, the synthetic data, it shows the um, intra they are forming clusters clearly and visibly. And another is to study the performance of these clusters. So we want to compare different indices. One is using internal and other is using the external validation matrices. These two are internal and these five are external. So one is for real data set and other is for the synthetic data set. So here, if you get the performance indices, larger the indices indicates that model is performing well. When you see here SI, it is a larger value, whereas DI is a smaller value as compared with the other. Similarly, for other, PWI is small, larger and others are also larger. So therefore, as a overall, this DPMM is performing better as compared with already existing models like GMM, K-means, DB-scan, and Triple M models. This is for Matwara data. Similarly, for Bay region, so we have considered internal and external data validation matrices and their indices. So here is also DI is showing in the DI, K-means is performing well, whereas for other situations, this DPMM is performing well. And third region, Kilimanjaro region, in this region also, DPMM is performing better than as compared with the already existing models. So from these tables and the clustering models, so we obtained that the developed GAN-based framework for generation of the synthetic data evaluates the better performance as compared with the previous one. And the, the main aim of this work is the DPMM model is performing better as compared with the existing models. GAN training faced instability model collapse and loss validation. That is also we have observed. Lower learning rate is from 0.00022 to 0.405. Increasing here we increase the batch size is 64 to 128. Updated ratio adjustment is 1 is to 1 to 1 is to 5. And also we have used the gaming initialization warming starting time. So as a whole, GAN achieved lowest risk in attributes membership inference. differential privacy leakages, KNN residentification. What is the use of this clustering? So when you make a cluster validation, so when you compare these models, DPMM for outperforming as compared with the other models. In that also, within that models, when you consider the internal matrix, SI is increasing, DI is decreasing, PWI is increasing, whereas in the external matrix, ARI is increasing, AMI is increasing, Jacquard and Federite ratios are also increasing. And other observation says when you compare this SI index and ARI, AMI, and these all are consistent for the DPMM model for both real data and the synthetic data sets. Synthetic data retains the latest structure smoothing. So when you observe these accurate multimodality pattern discoveries, presentation of regional heterogeneities, high alignment with real data clustering output, you could identify that the synthetic data retains latent structures. And as if at the end, one important identification is DPMM clustering is the better performing with the existing models. And also, when you see the multimodality clustering, like cluster 6, the cardio and neuro problems are enhancing the diabetics, whereas another cluster 2 is metabolic and respiratory problems are also adding to the this diabetics. And fifth cluster is cardio and metabolic system is also influencing for the uh, this diabetic patients. So these are the key findings from the DPMM model. So that is the end of the presentation. Maybe for future research work, one may consider these models, PAE for a parametric approach by using KL divergency and chi-square matrices, or maybe someone may consider that the improve scalability to complex data sets by using different pattern models. One may consider as a future research work. So these are the observations. These are the some references.
Thank you, Professor Rao, for the nice talk.
Yeah. Thank you, sir.
Any
Thank you
questions?
very much.
Any questions or comments from the participants, audience? Otherwise, let us thank the speaker once again. Thank you, sir. Thank you.
Thank you, sir. Thank you, sir. Thank you, Professor Loganathan, for nice
Next,
cooperation. Nice cooperation. I have another meeting, and so that's why I have presented. Okay.
our next
My
speaker is
apologies.
Professor Loganathan,
Yeah.
and he is
My apo-
from the Central
my
University.
apologies. My apologies. Let me leave the presentation.
Okay, sir. Okay, okay.
Okay. Thank you, sir. Thank you, sir.
Professor Loganathan, please.
Yes.
Well, good afternoon. Uh, Good afternoon to everyone. Am I audible, sir?
Yes,
So,
yes,
Srinivasarao, you
audible.
can close your screen so that I can share my screen. Srinivasarao.
Now it's up.
Huh? Is it okay?
Yes, sir.
Yeah, I think it's okay.
Sir, is the screen visible?
Yeah,
Yeah,
yes,
it
yes,
is.
it's visible. Oh, yeah. You can make it in full screen mode. If
Is it all right, sir?
okay, okay, okay.
Is the screen visible, sir, now?
Yes, yes, it's clearly
Right.
visible.
Well, good afternoon to everyone. Thank you, Professor Jayakumar, for chairing this session. I thank Dr. Satish Kumar and his team for inviting me to deliver a talk in this WSTA international webinar celebrating the National Statistics Day. Uh, this my paper is about development and analysis of multiple dependent state repetitive group reliability sampling plans based on exponentiated rally distribution. The title itself explicitly tells that it is about generation of sampling plans, development of sampling plans. They are the tools, statistical tools developed for conducting acceptance sampling exercise in product control division of manufacturing industries. When the quality characteristic is the lifetime of the product under inspection, then unlike the other sampling plans, the reliability sampling plans are very, very essential. In that respect, reliability sampling plans are evolved for each type of product when the lifetime of the product varies over the distribution, because the lifetime of the products may vary. The distribution of the lifetime of the products may vary over the products. Accordingly, different reliability sampling plans are required. And as an advancement in the development of the distributions, the development took place in the distribution theory, that introduction of new parameters in the power of the cumulative distribution function generated the new family of distributions called exponentiated distributions. For each kind of distribution, one corresponding exponentiated rally distribution is also exponentiated distributions are developed. In that respect, here in this paper, we assume that the lifetime product, the distribution of the lifetime product of the product is assumed to be distributed exponentiated Rayleigh distribution. And under that assumption, this paper attempts to develop or construct a multiple dependent state repetitive group sampling plan. This is the organization of my presentation. Initially, in one or two slides, I will share what is the operating procedure of the multiple dependent state repetitive group railroad sampling plan. It is a formal. It is a development of group repetitive sampling plans. Absolutely. And basic details about which are required to construct the sampling plans based on the exponentiated Rayleigh distribution will be shared in few slides, and how the plan parameters of that, in short, hereafter let's call this as MDSRGRS, multiple dependent state repetitive group sampling plans, as MDSRGRS. So what is the problem connecting with the designing of MDSRGRS? That will be displayed in two slides. And as a solution of that, we have developed an algorithm for determining the plan parameters as a solution of that decision-making problem. And an illustration is given. And efficiency of this multiple MDSR-GRS plan over other single reliability sampling plans are discussed with respect to sample size as well as risk efficiency. Finally, the properties of the MDSR-GRS plan under the exponential Rayleigh distribution is studied using the operating characteristic function of the plans. So this is the slide which exhibits the operating procedure of multiple MDSR GRS sampling plan. The sampling plan is defined with these parameters. Capital N, that is the lot size, small n, that is sample size, C1, C2 acceptance numbers, and K
Sir,
as a constant.
sir,
And the
excuse me,
constant
sir.
that we will
The,
come to. Sir,
the slide is not moving.
is it?
Yeah. Now it's okay. Now it's coming. Now it's coming.
Is it okay?
Is it okay? Okay, okay. Now it's okay.
So it's not moving.
The sharing is now stopped. You may have to share once more. I think it's once again. Now it's coming.
1 minute. Something technical.
ജേസൺ സാറല്ലേ സ്ലൈഡ് അനങ്ങുന്നില്ലേ? ഓക്കെ, എനിക്കൊന്ന്
It's not
എൻ്റെ സ്ക്രീൻ
scrolling.
But now it is in the second slide.
Yes,
Organizers
sir.
of the presentation.
Yes, sir. Yes, sir. I could see, but I want to move to the next slide.
Yeah.
സാർ
This is the third slide.
Yeah.
This is the operating procedure of the sampling plan. The plan parameters are uppercase N, that is the lot size, small n is the sample size, C1, C2 as the acceptance numbers, and K is the constant. According to this plan, how the plan is executed, is operated is random sample of n items are selected randomly from the lot consisting of capital N items, and the sampled items are put for the live test, fixing the test termination time and T. It is not mentioned here. It is T hours, and the live test is conducted for all the sampled items, and the failures are observed. The number of failures is count and uppercase X. And if suppose the observed number of failures is less than or equal to the C1, the first acceptance number at time T, accordingly, then the current lot is accepted. If suppose the number of failures exceeds the second acceptance number C2, accordingly, at time t or earlier, not necessarily at time t, even before earlier, if the number of failures exceed C2, here between C1 and C2, C1 is smaller than C2. If X exceeds C2, then reject the current lot. On the other case, if suppose the number of failures lie between the C1, it is more than C1 but less than or equal to C2 at time t, then accept that the decision is taken based on the preceding k lots, the lot k lots preceding the current lot, and if all the k preceding lots are accepted subject to the acceptance criterion prescribed in this step 3. If any one of the k lots, any one of the lots in the preceding k lots are not accepted, then we will move forward. Then we will have to go for resampling. That's it. So these are the various attempts made earlier on developing the MDSR-GRS plans. The work initially initiated by Aslam and others, and the paper was published in the journal Quality Engineering for birth type 12 distribution. These are other attempts made on developing MDSR-GRS plans for various lifetime distributions. Birth type 12 distribution, exponential and variable distribution, and myself and my co-author of this paper, Dr. Gunasegaran, exponential, and inverse power Lomax distribution for Marshall Alkin logistic exponential distribution and gamma distribution. And these are the earlier attempts made on developing MDSR GRS plans. And in fact, in practice, we see that in the theory, we see that the MDSR GRS plans have overall sample size efficiency, risk efficiency. That is the reason why we are motivated to attend this work. So this is the exponentiated Rayleigh distribution. If suppose T represents the lifetime of the product and the exponentiated Rayleigh distribution, the probability density function has this is defined in this way, and the cumulative distribution function of this lifetime product, the random variable lifetime, is this one. In fact, this is the 1 minus e power half minus half times of t over lambda whole square is the Rayleigh distribution, cumulative distribution function of the Rayleigh distribution, and its power is raised to the parameter theta that generated the exponentiated Rayleigh distribution. In fact, the distribution is defined based on the cumulative distribution function first. From then, it is the probability density function is evolved as next. You can see these are the graphs showing the behavior of the probability density function of exponential Rayleigh distribution for fixed lambda and for varying values of theta. As and when the value of theta keeps increasing, you can see that the distribution becomes it has long tail on the right side. It is more skewed, and for this kind of a distribution, the decision based on the decision. The construction of the sampling plan in reliability sampling plan is usually for other distributions, they are done based on the mean of the lifetime distribution. But here, since the distribution has a longer tail, it's a skewed distribution, we use the median as the criterion to develop the sampling plans. Median of the exponential Rayleigh distribution is derived in this way, and since it involves this lambda and theta, and we are going to develop the sampling plans for prescribed level of median lifetime by producer as well as consumer. Rather than having these two parameters, lambda and theta, we fix the theta and we determine lambda for every given m and the fixed theta. So this is the lot quality we define, because we need the lot quality at producer's level as well as consumer's level for developing the sampling plan. This is the lot fraction non-conforming, the lot quality prescribed for the exponentiated Rayleigh distribution. The value of the lot fraction non-conforming is evolved from the cumulative distribution function at T over M. So T is the test termination time, M represents the median lifetime. corresponding to the median lifetime prescribed by the producer's level, the AQL is calculated using this equation, the value of P1. Similarly, the corresponding to the median lifetime prescribed for the consumer's level, the LQL is the value of LQL, that is P2, is evaluated from this equation corresponding to this M2. So for every given set of T, theta, M1, M2, we evaluate the AQL and LQL values for calculating the value of the accept for calculating two are not no more new. The left hand side of these two inequalities are none other than the value of the operating characteristic function of the MDS or GRS plan corresponding to the given exponentiated Rayleigh distribution. And the expression for the ASN function, ASN function for this case is this one, is given at the bottom, at the end of this slide. N over 1 minus probability of C1 x less than or equal to C2 times 1 minus probability of x less than or equal to C1 upper, raised to the power k. The value of this probability, the probability values will be calculated corresponding to the distribution which we are going to assume for this x. X is the number of failures. So for the number of failures, what the distribution we are going to assume, whether it is binomial or Poisson, accordingly, the values of these probabilities and the corresponding OSA function values and the ASN function values will be evaluated. In order to solve this problem, we developed an algorithm, and the algorithm is presented here. That in the stepwise process, this is the stepwise algorithm for solving that the optimization problem for finding the values of n, c1, c2, and k. At first, we calculated the values of lambdas for corresponding to, there is only one lambda, but however, for each value of m1 and m2 correspondingly, we calculate two lambdas, lambda 1 and lambda 2. Corresponding to them, we calculate the value of AQL and LQL. Of course, these expressions which we presented in the previous slides, we calculate the values of AQL and LQL. This is none other than the evaluation values of the model parameter lambda for two different levels of M1 and M2, and for evaluating AQL and LQL values. Then set the value of k is equal to 1, and set the acceptance number C1 at 0 and C2 at C1, C2 at C equal, and proceed to evaluate the values of n with NL satisfying this condition, that is producer's condition, and find out the smallest n value, that is ns, corresponding to this consumer's condition. Corresponding to them, find out the values of NL and NS. When you find that NS is less than or equal to NL, then the optimum plan is NS C1, C2, CK. Of course, NS is smaller, that is taken here, NS C1, C2, K. And if this is the case, this is the optimum plan, and we can proceed further. We can set the value, we can increase the value of K to the next one, that is K is equal to K1, K is equal to 2, and we can proceed evaluating executing these steps. In case, if suppose NS is not found to be less than or equal to NL, rather bigger, then we increase the value of C2 to C2 to plus 1, and we repeat this procedure. And at first, when we find that NS is less than or equal to NL, that will be the optimum plan. If suppose this condition is not satisfied, then we increase the value of C1 with one increment, with one acceptance number. C1 is increased by 1. And we repeat the steps again until we get the values of NS is less than or equal to NL. Once we get the NS is less than or equal to NL, corresponding to them, we evaluate the value of ASN. And after finding the ASN value, again we increase the value of K with 1. We repeat it again and again. And finally, we may have different combinations of this NS C1, C2, K. For the same set of P1, P2 or alpha, beta, we may have different combinations of NS C1, C2, CK. At that time, we use ASN as a criterion to choose the optimal plan, that the quadruplets of this one corresponding to the smallest value of ASN will be the optimum sampling plan. So this is the development of the algorithm, and the algorithm is, the flowchart of the algorithm is presented here. I do not know whether it is visible. I tried my level best. So this is the flowchart, the execution of that algorithm. illustration of the application of this algorithm, assuming that the number of failures follows binomial distribution. So here we have taken the median lifetime prescribed by the producer's level at 1,700 hours and median lifetime prescribed at consumer's level at 800 hours. And alpha is 0.05 producer's risk and consumer's risk is 0.1 and test termination time is for 450 hours. Corresponding to these and application of the preceding algorithm, we found that the optimum MDSR-GRS plan under the conditions of exponentiated Rayleigh distribution as 24,012 corresponding to T is equal to 50 hours. It means that the sample size is 24, the first acceptance number is 0, second acceptance number is 1, and the successive preceding lots shall be 2. Corresponding to that, how are we going to execute? How are we going to execute the plan? The plan will be executed in this way that we will select 24 products randomly from the lot submitted for inspection. From that, for all those 24 products, the life test will be conducted, fixing the 450 hours as the maximum test termination time. And if no failures occurs within 450 hours, the life test will be stopped and the lot will be accepted because C is equal to 0. On the other hand, if suppose more than one failure occurs within 450 hours, the life test will be stopped and the lot will be rejected. In the other case, if it is within 450 hours, only one failure exists exactly, then the current lot will be accepted corresponding to the decision taken for the preceding two lots, considering the acceptance criterion for the preceding two lots. If though preceding two lots are accepted, the current lot will also be accepted. Otherwise, the process will be repeated again. Then efficiency. As far as the efficiency is concerned, corresponding to these specifications are producer's risk 0.05 and consumer's risk 0.10 and 450 hours as test termination time and theta is equal to 2. For different levels of producers median lifetime and consumers mean lifetime, the plan parameters are determined for MDSR GS plans. They are presented in the fourth column, 24, 37, 52, 73, 120, and the corresponding A's and values are presented in the next column. When the corresponding to the same specifications, the single reliability sampling plans are determined, and the plan parameters are N is equal to 42, 68, 93, 126, 179. Though the lifetime of the product follow the exponentiated Rayleigh. These are the reliability single sampling plans developed under the conditions of exponentiated Rayleigh distribution. When we employ MDSR-GRS plan, how much reduction we will get corresponding to the sample size. Accordingly, the time as well as the cost of conduct of the experiment will also be reduced. There is a greater reduction in the sample size here. And corresponding to the risk efficiency, so this is the risk efficiency evaluated for comparing the efficiency of MDSR-GRS plans with the single sampling plan. Why we compare this? Because the reliability single sampling plan is the simplest one which we use to develop. So how efficient this MDSR-GRS plan is, that we can see here that. So for the same set of specifications, the plan parameters are developed for RSS as 79.1 and for MDSR-GRS as 52.0.1 and 2. Corresponding to the same set of P1, P2, we see that the exact producer's risk is 3.38 for RSS, reliability single sampling plan, whereas it is greatly reduced for under the condition by MDSR-GRS plan. Correspondingly, we can also see that there is a reduction in consumer's risk also by the implementation of MDSR-GRS plan. So in total, since both, sometimes it may so happen that producer's risk may be lowered and the consumer's risk may be oscillating. But here in this case, we see that in both the cases, producer's risk and as well as consumer's risk are greatly reduced. And as the properties of the MDSR-GRS plan So behavior of the operating characters function is studied with respect to the characteristics which influence the operating character, which are considered for the evaluation of the operating characters function, because they are all the influences for the determination of n, c1, c2, and k. Here we have the thing that basically the lot quality is determined based on the value of T over M from the expression of P. We have developed, we have shown that expression for this P, which is a function of T over M. T is the test termination, it is the ratio of test termination time to the median lifetime. And it is observed that, of course, I did not show it, but when it is observed that T over M, P is a monotonically increasing function of T over M. When T over M increases, P increases. When the lot quality becomes deteriorating, not naturally, the lot acceptance probability shall deteriorate. The lot acceptance probability shall decline. So this is exhibited here in this case. So the x-axis represents the value, exhibits the values of T over M. Correspondingly, the corresponding values of P of P, lot acceptance probability, are located along the y-axis. So when T over M is increasing, the ratio of test termination time to median lifetime increases, the lot acceptance probability decreases.
Sir, 5 minutes more.
Sure, sir. I'm coming to the last 5 slides. Of course, it is a supplement to the preceding slide. Since P is a monotonically increasing function of T over M, naturally, when the test termination time increases, correspondingly, the same behavior of the lot acceptance probability is also observed. And in turn, since M is in the in the denominator of this T over M, the process, the behavior will be reversed. When M, the value of M is increasing, the P of P will be decreasing. So this is the behavior of the lot acceptance probability corresponding to the increasing values of this M. And then the value of n, when it is a well-known fact that when the sample size increases, when the sample size increases, there is a larger quantity of failures may occur. Accordingly, the lot acceptance probability will decline. That is observed from the behavior of the operating characteristic function. Similarly, for the acceptance number, when we allow more number of failures, when we allow the number of failures to increase, the acceptance number to increase, naturally lot acceptance probability will also increase. That is the case for both C1 as well as C2. As far as K is concerned, we could not find any pattern or behavior of lot acceptance probability based on the increasing value of this K. It seems that K does not have influence upon the behavior, upon the value of the operating characteristic function. The properties of operating characteristic, studying the properties of operating characteristic function are very, very essential to understand the determination of the plan parameters. So that is the reason why we studied all these things. And we come to the last slide. Thank you, sir.
Thank you very much.
I have completed my presentation. Of course, I found a technical problem in presenting my slides. My system does not cooperate. However, I tried my level best to show the slides. Please, sir.
Yeah, it was very nice and readable. It's very fine. Any questions or comments from the audience, please? Guys, let us thank the speaker once more. Thank you, sir. Thank you very much.
I thank Professor Jay Kumar for chairing this session and Dr. Satish Kumar and his team for giving me an opportunity to present my work co-authored by Dr. Gunasegaran. Thank you, sir. Thank you for your passion for listening. Thank you.
we have a very nice, very excellent session earlier. Professor Laganathan sir and Professor Gede Srinivas Rao. And
And I take this opportunity to congratulate you, sir, for consistently organizing this WSTA and ICSTC consistently. Congratulations.
thank you, Professor. Thank you so much. And we are very much thankful to you, Professor, for your support, blessings, and all cooperation in that.
Sure, sir.
Thank
Thank you.
you. Thank you. And also, we wish to thank our chair, Dr. Jayakumar, Professor Jayakumar, for the nicely managed session. Thank you. Thank you. And in fact, we have now the 3:52. Okay. Now in the next session, we begin by 4. Within by the time 2-3 minutes we can take, or any discussions if requires. I would like to know whether the chair of the session was Raghavendra Sharma, and the speakers, Professor Hariharan Lunche, Devendra Kumar, available. Sorry, no. Hi, Professor.
Sir, namaskaram, sir.
Namaskaram. I just noticed you are here.
Sir, hello, how are you?
Fine.
Sir. Now paper presentations are there, sir. Otherwise, there is lectures.
Yeah, now the other invited lectures, the other one.
Okay.
Any more, Professor? How is Hyderabad?
So going on, sir.
Okay.
Moving slowly.
Oh.
But we should be always congratulate you.
Yeah.
Because you are very active role in this era of statistics.
Now,
Really.
because of the blessings of you.
No, sir. Your hard work, and your good relations with all the people. It's really, really great. Because since I'm sincerely contact with almost all 30 years, happen to be see these statistics.
Thank you, sir. Thank you for your compliments.
This is really good. I think nowadays the people are running away from the. I'm sorry to say.
I
just wanted to say hello to
Madam,
you.
namaste.
Nalini. My name is Nalini.
Yeah.
Sorry, I'm missing a lot of your conference. I just woke up and I got my coffee and I came and I thought I will listen.
No, please join with us whenever you are getting
I'm
time.
I'm very pleased to, and I hope to see you this December, Satish. So maybe
Yeah,
this
please.
December when I visit, I'll
Great,
text
great.
and we can meet.
Great. Thank you.
I don't know you, Raghavendra.
Sir,
I don't
Madam,
think.
Namaste. I am Dr.
Call
Raghavendra
me
Sharma.
Nalini, please. Yeah.
Yeah, I am from Usmania University, Department of Statistics, madam.
Ah, very nice.
I'm happen to
What do
be
you
there
have?
from last 30 years.
Oh, nice. I have been at University of Connecticut for more than 30 years now.
Oh, super. Excellent. No.
What about the Professor Hariharan? The speakers of the session are already joined? Available? Professor Hariharan?
Sir, is
Yeah.
there?
Hi, Professor. Hi.
Good evening, sir. Good evening.
Good evening. Good evening. You are waiting. We are-
Yes, yes, yes.
Now I think so we can move to the session because by the time introduction etc. Takes place. Um, I think to Devika.
Yes, sir.
Devika, please introduce the chair and support the chair for whatever needs for the smooth run of this session. Please. Welcome,
Good
Professor.
evening. Good evening, everyone. It gives me great pleasure to welcome you all to the 18th technical session of the 10th International Webinar on Recent Trends in Statistical Theory and Application. We are honored to have with us as the chair of this section Professor Raghavendra Sharma from Osmani University. Professor Sharma is a distinguished academic in the field of statistics known for his dedication of teaching, research, and academic leadership. His areas of expertise include statistical inference, distribution theory, and stochastic process. We are grateful for his guidance and leadership in this section. It is also a distinct privilege to welcome our invited speakers, both of whom are contributing important work in statistical theory and applications. First, we have Dr. Harihar Sriram Lunje from Sri Shivaji Science College, Amaravati, Maharashtra. Dr. Lunje is actively engaged in research in stochastic process and decision theory. His contribution in Markovian models and related decision frameworks have been well received in the academic community. He will be representing he will be presenting on the topic title on Markovian decision process. Dr. Lunje, we are delighted to have you with us. Next, we are pleased to welcome Dr. Devendra Kumar from the University of Delhi, India. Dr. Kumar has been working in the areas of statistical distribution theory and survival analysis. His research includes inference under censoring, stress models, and Bayesian approaches. He will be presenting on the topic inference for chain distribution under simple step first case in the presence of censoring. Dr. Kumar, we are equally delighted to have you with us. We are privileged to have both our esteemed speakers with us today and look forward to the insight they will share. With that, I now invite Professor Raghavendra Sharma to kindly take the section forward.
Thank you, madam. Thank you, sir, for giving me an opportunity to share this session in this wonderful series of contents, I think. Sir, you're most welcome, sir. So, I don't have any list now.
Professor, yeah, we have two speakers. Yeah.
Yes, sir.
I have already sent you can that in the WhatsApp. I think
Yes, sir. I will.
the program schedule just you can mention
Yeah, yes, sir.
and invite, and thereafter you can.
This is on the 18th one, sir.
Hello.
Sir, you're most welcome, sir.
Okay. Okay. Thank you, sir. Very first,
Yeah.
I am very much grateful to the Dr. Satish sir and the chairman of this session, Raghavendra sir.
Sir.
Other speaker also from Devendra, the Delhi,
Sir.
and all the audience, the dear participants. It's a very good activity organized by this Kerala University, particularly Dr. Satish sir. I am continuously in touch with the academic activities of this Kerala University, the Department of Statistics, under the leadership of Dr. Satish sir. And this is a very good occasion about the National Statistics Day. And on this eve, the 4-day international webinar series is very good activity for all the statisticians all over the world. Personally, I am very much thankful to the Dr. Satish sir that I have been given the chance as I retired in 22 from the Shivaji Science College as a professor in statistics and as an accuracy coordinator. This Shivaji Science College is our NAC accredited A plus in fourth cycle, and I was the accuracy coordinator. This is the top one college in Santa Gadge Baba Amravati University, Amravati. And also this our college under the NIRF ranking, 99th rank in the last year. Before that, 150 to 200 rank band. Okay, so this is the just general information, but I'm not working in the university, but our college is affiliated to the Santa Gadge Baba Amravati University. My research field is the operations research and statistical method. Under the operations research, we have the dynamic programming. And under the dynamic programming, the use of the dynamic programming in the Markovian decision processes is very much used. So I start my presentation. So this Markovian decision process involves the optimization with the stochastics transition probabilities. And the solution of this stochastic decision problem, which described by the finite number of states and can be obtained through the dynamic program. The transition probabilities between the states are described by the Markov chain. The reward structure of the process is also described by the matrix whose individual elements represents the revenue or the cost resulting from the moving from one state to another. Both the transitions and the revenue matrices depends on the decision alternative available to the decision maker. Both the decisions here about the transition and the revenue matrices depends on the decision maker. Hence, the objective of MDP, that is Markovian decision problem, is to determine the optimal policy which maximize the expected revenue of the process for the finite or infinite time. No doubt this Markov decision problem is a powerful tool to analyze the probabilistic sequential decision process with the infinite planning horizon. The basic idea of the dynamic programming is the states, principle of optimality, and the functional equations. The functional equations is obtained from the principle of the optimality, stating that it has a property that whatever the initial states and the initial decision, the remaining decision must constitute the optimal policy with regard to the state resulting from the first transition. The author, all we know that the word in 1960 used this basic principle from the Markov chain, that is the combination of the Markov chain and the dynamic programming, to develop the policy iteration algorithm for solving the probabilistic sequential decision process with the infinite planning algorithm. In many fields, in these various fields,
Interrupt, sir. Sorry to interrupt. You are sharing the screen, but it is only the showing the title. Are you scrolling the screen, sir?
just a minute, just a minute.
Yeah, sir. Please.
Hello, it is that. Someone just slide on me the title.
Sir,
Just a minute, sir. Just
you have a see there is a margin one, two, three, four, five sheets are there. You just click the sheet. It
okay.
automatically it will come. You two is there. Once again you can share the screen. Yeah. Now it is okay, sir. Yeah, now it is.
Okay. Now it's changing, sir?
Yeah, it is changing.
Oh, yes, yes, yes. Okay,
Yes.
okay. Thank you, sir.
Sir, you're most welcome.
Okay. So as we discuss here, that this Markovian decision processes has the applications in the various field, and no doubt the Howard using the Markov chain and the dynamic programming, Howard developed this policy iteration algorithm for the probabilistic sequential decision process. And in any field and in the two types of the decision problems may arise: finite stage and infinite stage. And there are the two methods for solving the infinite stage decision problem: exhaustive enumeration method and the policy iteration method. Here in this article or here in this discussion, I will discuss about this policy iteration method which developed by the Howard. The Markov decision problem has many potential applications in the marketing, in inventory, in maintenance of the machines, in resource allocation, in computer science, and also more familiar to the engineers and the OR analysts. The policy iteration is generally employed to identify the optimal policy through the iterative approach that alternates between the policy evaluation and the policy improvement, and progressively defining the policy until the optimality is achieved. In deterministic system, the process of the value iteration and the policy iteration provide the effective framework for addressing these challenges. Value iteration and the policy iterations are the two popular techniques used in the dynamic programming to solve the Markovian decision process. In this article, sir, we propose the modified form of the policy iteration method. So whatever the earlier policy iteration method, so after many observations and many calculations, we found some improvement in this policy iteration method. So we propose here some slight modification in the policy iteration method which overcome the drawback of the original policy method. And then I will illustrate the policy with the comparison of the results of the both the methods, considering the former example. Here this original policy iteration method without discounting. So there are the two types of the policy iteration method, with discounting and without discounting. So here I consider here without discounting factor. The original policy given by the Howard, very first step, very first step is to choose the policy arbitrarily. So whatever the various stationary policies are there, 2, 4, 6, 8, whatever the up to n, out of that, the Howard suggests to select the policy arbitrarily and then goes to the value determination step. So use this equation ES VIS plus summation PIJS Fj minus Fi. where M is the number of the states for each stage and E is the expected revenue. And using this value iteration, value determination step, it goes to the policy improvement step by this equation. And then finally, optimum decision K for the state 1 to M constitute the new policy T. If S and T are the identical, then the algorithm stop. And T policy will be the optimum if S and T are identical. Otherwise, set S equal to T and then again return back to the value determination step. So this is the original policy iteration method without discounting, where only the two steps are main, that is value determination and policy improvement. And very first starting of the algorithm is to select the policy arbitrarily, yes. So here giving many thoughts and observations and by calculations, we propose here one slight modification, that initially selecting the policy arbitrarily, instead of selecting the policy arbitrarily, we select the policy judicially. That here we propose initially to start with the policy by using the maximum of VIK, where VIK represent the expected return from the single transition. So VIK will be summation Pij Rij. No doubt Pij are the transition probability from the state I to J, and Rij denote the return function corresponding to the Pij. So here this is one modification that we propose in the original policy iteration method, that instead of selecting the policy arbitrarily, when there are the large number of the stationary policies in any type of the situation, in any types of the problem available, so in that case, if we select the policy arbitrarily, then the computational work will be more and number of iterations will also be more. Therefore, we suggest here that select the policy judicially. So here we propose this modified policy iteration algorithm that obtain this VIK. So we have the Pij, that is the transition probability matrix, and Rij, the return matrix for whatever the various policies are there. And after obtaining this VIK, we select the maximum of VIK. So we select the stationary policy S, for which VIK gives the maximum. We select the stationary policy S for which the VIK gives the maximum value. And then the second step and the third steps are the same. Second step, that is the value determination step, and next step is the policy improvement step of the original policy iteration method, are the same. So we propose here this slight modification in the original method by, without selecting the arbitrarily, select the stationary policy finding maximum of VIK. Second step is no doubt, so whatever the stationary policy is selected, so corresponding to this stationary policy S, we will have the PS, that is transition probability matrix for that stationary policy, and RS. And assuming here FM0 and solving the equations in the M unknown. We have the M equations there, M unknowns, ES, F1, F2, Fm minus 1. So solving the equations, and then we find this ES, value determination step, and then go to the policy improvement step. Then for each state I, we obtain this maximum of K, VIS plus summation Pij, Fsj. And finally, the resulting optimum decision K for the states 1 to M constitute the new policy T. and the step second, that is value determination step. So we have to continue this cycle till the optimum policy reach. And finally, the objective function, that is our main objective that earlier we have discussed, that we have to maximize the revenue. So to obtain the maximum value of the function E, that is revenue, so this will be E mu plus summation Pij Fj minus Fi. And using this, we can obtain the maximum of this. Now here, this modification, we consider here one simple farmer example. In the agriculture farm, one farmer, at the beginning of the farming session, farmer applied the chemical test to check the soil condition. And he applied the chemical test. And depending on the outcome of the chemical test, the farm's productivity for the new session is classified. So the productivity of the farm is classified in the three states: good, fair, or poor. And this productivity depends on the chemical test, outcome of the chemical test to check the soil condition. So every year the farmer has this methodology. Over the years, the farmer observed that the current year productivity can be assumed to depend on the last year soil condition. Current year productivity of the product, any crop, is depends on the previous year soil condition. So soil condition depends on the chemical test applied by the farmer. So as the soil condition change, the productivity of the particular crop will shows the increase or decrease. So this productivity we classified in the three states: good, fair, or poor. So transition probabilities over 1 year period from one productivity state to another can be represented by the Markov chain. So here we have the Markovian. So this problem becomes the Markovian decision problem. So here we assume that there are the three states, 1, 2, 3. So we denote by 1, 2, 3. 1 as a good, 2 as a fair, and 3 as a poor. So after applying the chemical test by the farmer, the soil condition is good, we denote the state 1. If soil condition is fair, we denote by the state 2, and poor then 3. And here for the first year, this is the transition probability matrix. So system of state of the system this year and state of the system next year. So we have this transition probability matrix. Now this transition probability that shown in this P1 matrix. So this P1 indicate that productivity for the current year can be no better than the last year. Productivity for the current year can no better than the last year. For example, if the soil condition for this year is fair, next year productivity may remain fair with probability 0.5 or become poor with the same probability 0.5. We can observe here the second row. Fair, it will not become the good because that probability is 0. So if the soil condition of the current year is fair, next year productivity may be fair with probability 0.5 or may be poor with probability 0.5. Now farmer use the fertilizer to boost the soil condition. Now farmer has these two choices, two actions: to use the fertilizer and do not use the fertilizer. So farmer has the two choices and three states. That is about the soil condition: good, poor, and fair. So farmer use the fertilizer to boost the soil condition. Hence the farmer can alter the following transition matrix P2 when the fertilizer is used. The previous P1 gives where the no fertilizer used, and in the next year suppose the farmer use the fertilizer to boost the soil condition, then the transition matrix become in this way. 0.3, 0.6, 0.1. No doubt, as per the Markov chain, the sum of the rows of the probability summation Pij is 1. So this will be the P2. So P1 is the transition probability matrix when the farmer do not use the fertilizer, and when the farmer use the fertilizer, this transition probability matrix become P2. So farmer associate the return function with the transition from one state to another. So the return function expresses the gain or the loss during the 1 year period depending on the status between the transition is made. Now since the farmer has the option of using or not using the fertilizer, gain and loss are expected to vary depending on the decision made. So these matrices, gain or loss, the matrices R1 and R2 gives the return function in thousands of the rupees associated with the matrices P1, P2. So associated with the P1, R1 gain matrix and R2 related with the P2. So R1 applies when no fertilizer is used and R2 is when the fertilizer is used. So return function. So this will be the return function R1 and R2. So when the fertilizer is used in the R2, so that will be the cost. The elements in the R2 takes into account here the cost of applying the fertilizer. And in R1, the gain of the product. Now here the farmer has to think about the decision. Farmer has the two actions to fertilize and do not fertilize, and the three types of the states: good, fair and poor. So what kind of the decision problem does the farmer have? So first we must know whether the farming activity will continue to limited number of years or for all practical purposes indefinitely. So this situation here, the finite stage and infinite stage decision problem. In both the cases, whether it may be the finite stage or the infinite stage, in both the cases, farmer would need to determine the best course of action. Best course of action means to fertilize or do not fertilize. Given the outcome of the chemical test, that is the given the outcome of the state of the system, that is the soil condition, good, fair or poor. So here the optimization process is based on the maximization of the expected revenue, and farmer may also interested in evaluating the expected revenue resulting from the following pre-specified course of action whenever it is given state of the system. For example, fertilizer may be applied whenever the soil condition. fertilize whenever the system is in the state 1, fertilize whenever in the state 2, policy fifth, fertilize whenever the state 3. In this way, we have these 8 different stationary policies and corresponding the transition matrices. So as we have seen the P1, P2, P1, P2 and R1, R2. So using the P1, P2, R1, R2 and with these stationary policies 3, 4, 5, 6, 7, 8. So we obtain the stationary matrix, transition matrix P3, P4, P5, P6, P7, P8 and similarly R3, R4, R5 and R6, R7, R8. These matrices. Now these all the 8 matrices are used. So here using the original policy iteration method, which indicates that select the policy arbitrarily. Suppose arbitrarily we select the policy first, do not fertilize. So when the policy first is selected, then corresponding matrices will be P1 and R1. So P1 and R1, using the P1 and R1 and using the value determination step, we have the equations. And after solving these equations and setting F3 and F2 values, we obtain the policy improvement steps. Corresponding matrices of the policy 2, that is P2 and R2. So again P2 and R2 are used and we got this equation. After simplifying this equation, we got this E equal to 2.26, F1 6.73, F2. So here E is the expected revenue, which is increased 2.26. Earlier here E was -1. In the very first step, expected revenue was -1. Now in the second step, the expected revenue E is increased to 2.26. And now again using this E value, F1 value, F2 value and VK values, we obtain this second policy improvement steps. So K equal to 1, we got this 8.54, 8.4.89 and for K equal to 2. Similarly here, optimal solutions, that is maximum value from the K equal to 1 and K equal to 2. So maximum values are about second policy K equal to 2.
Sir, 1 minute. Sorry for interrupting you. Sorry, already almost all time is reaching
Okay,
about
okay, okay. Just
30
yes,
minutes
yes,
because
yes.
next
I am
speaker
finishing
is
just 2 slides.
yeah,
Okay,
please,
okay.
please, sir. You don't
So
mind.
this we got the new policies 2 and which was the same to that of earlier one. So here we received the second policy. Earlier policy was also the second policy. So here the S and T policy, yes, earlier policy and new policy is the same. Therefore, this final policy. Second is the optimal and
No, no.
after
How many
applying
years
chemical.
is this? My question is, how many years is this ongoing? 10 years, 20 years? What is the?
No, 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 no. He will check up to the 2 or 3 years. That is, we have suppose two actions only. So do not fertilize and fertilize. So if fertilize, then next year he will fertilize. On the first year, suppose he do not fertilize, then he will have the something whatever the revenue obtained from the crop.
So
And
how did
second
you
year
get the transition probabilities? How were
transition
those numbers?
probabilities, transition probabilities are given by the or decided by the farmer, that he has that judgment that after using the fertilizer and suppose the soil condition is good, then the next year soil condition productivity will be good, that he has suppose 0.6 probability, or if it will be the fair, the probability he assume that it will be 0.3, that next year the productivity will be fair, or productivity will be the poor. He has that experience. So about that experience, he has that probability. So the probabilities are transition probabilities are obtained by the experience.
Okay, thank you.
Okay, thank you,
So any
sir.
more, any more questions, please? Yeah. Any more?
experiments. So in this study, we focus on the statistical estimation problem for chain distribution under a simple step stress ELT model with type 1 hybrid sensing. So the chain distribution introduced by Chain in 2000 is a flexible lifetime distribution that is well suited for modeling data with bathtub shape hazard rate characterized by an initial decreasing failure rate, a constant middle phase, and an increasing failure rate at the end. So this makes it applicable to wide range of real world system such as mechanical component, biomedical device, and electronic equipment. So the probability distribution, cumulative distribution, Hazard rate function of a random variable t follow chain distribution with parameter alpha and theta given by in the equation first, second, and third respectively. So the several authors have contributed to the estimation theory of the chain distribution. So this is the graphical representative of the probability density function hazard rate for the behavior of the PDF and hazard rate for different value of the parameters. So, so we can see that in the hazard rate is behavior as a bar top shape characterized by the initial increasing and decreasing, initial decreasing failure rate, a constant middle phase, and an increasing failure rate at the end. So many author statistical inference on the chain distribution like Saran et al. 2012 discuss maximum likelihood estimate and Bayes estimate by taking gamma prior using Lindley approximation method of unknown parameter of chain distribution, and also perform simulation study for comparison between the maximum likelihood estimate and approximate Bayes estimator under non-informative prior assumption. Wu et al. 2004 proposed the simple and exact method for conducting a statistical test for unknown shape parameter for chain distribution with hybrid sensoring. To work with step stress ELT of chain distribution, one can follow the recent work by Jian and Zhu in 2022. And for more work on chain distribution, one can refer the Ahmad 2014, Jang and Chung 2018, New et al. 2023, and Singh et al. 2023, and Kyle et al. 2020. So accelerated lab testing, in an accelerated lab testing experiment, the experimental units are subject to higher stress level than the normal operating conditions. It affects the life of the item under consideration negatively. Hence, the item fail quickly than under the normal operating conditions. So the factor that affect the lifetime of an item are called stress factor. For example, voltage, temperature, and humidity could be stress factor of electronic equipment. Some key reference of ALT are Nelson 1980 and 2009, and Meeker et al. 2022. So ALT can be generally characterized into three types based on the step application mechanism. So constant stress, step stress, and progressive stress. So the ALT experiment may be performed either at a constant stress, step stress, and progressive stress level. In constant stress, ALT unit are tested under a fixed stress level throughout the experiment. However, the choice of the stress level is critical. If too low, few or no failure may occur. If too high, the test may become economical unfeasible. So to overcome these limitations, step stress ALT introduce stress level increment at predefined time intervals. Especially in a step stress ALT, unit began testing under an initial stress level, and the stress increase once at predetermined time. And progressive stress ALT is constant, involve a continuous increase in a stress level, often requiring higher resources investment. So another challenge in ELT experiment is the presence of censoring, which arise when exact failure time are not observed for all unit. So common censoring scheme include type 1, type 1 and type 2 progressive censoring. In type 1, fixed time termination, and type 2, fixed number of failures. Each has limitations. Type 1 may yield insufficient data, while type 2 can be time intensive. So hybrid censoring introduced by Epstein 1954 addresses this by combining both scheme termination and experiment either at a pre-specified time or upon observing a pre-specified number of failure, whichever occur first. So this approach has been adopted military standard, and also a Balakrishnan et al. 2020-23. So next we move to the model setup. The aim is to insufficiently collect failure time data from a group of n test unit exposed to sequential stress level x1 and x2, where x2 is greater than x1. Initially, all the test unit are replaced under the lower stress level x1, and at the predetermined moment tau 1, the stress is elevated to x2. So we assume that the lifetime follow a chain distribution where parameter alpha and theta I, distribution where I run equal to 2, correspond to the two stress levels x1 and x2. The shape parameter theta is considered invariant across stress condition, while the scale parameter theta 1 theta 2 vary with stress. To relate these scale parameter to apply the stress, we adopt a log linear relationship, that is log theta equal to a naught plus a1 xi lies between 0 and 1, where a naught and a1 are unknown coefficient to be determined. To approximately link the effect of stress change over time, the cumulative exposure model is employed. See Miller and Nelson 1983. So under this model, the CDF of the lifetime denoted G theta alpha is defined by in the equation 4. Here tau 1 represents the stress changing time, and delta I is the correction term ensuring the continuity at the stress transition is chosen such that f of delta theta 2 alpha equal to f of tau 1 delta alpha equal to f of tau 2 alpha. And where Si equal to N1 plus I plus delta minus tau 1, I running from 1 to 2 up to N2, and St equal to T plus delta minus tau 1. Now on the differentiate the log livelihood function given equation 6 with respect to A naught, A1 and alpha by equating to 0, we get the following livelihood equations. Respect depending with respect to A naught, A1 and alpha. These are the some mathematical calculations A1 cap, alpha cap of A naught, A1 alpha respectively can be determined on solving the likelihood equation simultaneously. So it can be observed that the MLE do not turn out to have a closed form. So some numerical techniques such as Newton-Raphson method can be used to calculate the MLE in iterations. And the convergence of iteration can be reached on getting this is the mathematical equation which is less than epsilon for some given small fixed epsilon value. Here beta k represent the value of the parameter at kth iteration. Next we discuss the construction of the interval estimation. So this is the interval estimation. We construct the asymptotic confidence interval for unknown parameter based on the observed Fisher information matrix. Let beta equal to the A naught A1 alpha denote the vector of the parameter to be estimated. The observed Fisher information matrix is obtained by taking the negative of the Hessian matrix of log likelihood function. So this is the associated highest positive density HPD credible interval or HA naught A1 alpha using the generated sample. Let us assume that H1 H2 Hn minus 1 denote the ordered value of Hm plus 1, M plus 2, and so on Hn. And the asymptotic uh, the confidence interval is given as this mathematical equation. Then using the algorithm by Chen and Sao 1999, the 101 minus sigma percent, where sigma less than 0.1, HPD credible interval is given by this. So next we consider the simulation study by using the R software. So we generate the data set from Chen distribution taking into account the initial value such as A0, 0.5, A1, 0.7, alpha 2, that is theta 1, theta 2, and alpha 1.89, 3.33, and 2 for sample size n equal to 30, 40, and 50. So for this setup, we consider M having 20 and 40 censoring percentage using x1 0.2 and x2 1 as stress level and prefix state changing time tau 2 equal to 1 with two different value of termination time of experiment tau 1 equal to 0.2 and zero point 0.4. So for Bayesian setup, non-informative prior and informative prior are taken into account. We choose the hyperparameter value of the prior one, then mu1, mu2, this equal to 1, and hyperparameter values prior to taken mu1, mu2, and mu3 and nu3 is 1 when alpha naught a1 equal and a naught a1 and alpha zero point 0.5, zero point 0.7, and 2 reflect the prior knowledge about the parameter. Of failure time. There are four stress level in this data set, and each stress level has been taken into account by increasing the flow rate 5 centimeter per second in every 20 minutes. So this data set is also analyzed by Nasser et al. 2021 and Datta et al. 2023 for simple step stress case. So for illustrative purpose, we consider this data set as a simple step stress data set by assuming the first level as initial stress and merge other remaining stress level into one. For computation purpose, the data set value have been subtracted by 50 and divided by 150 respectively. The transform data set is tabulated in table 4. So to check the goodness of fit this data set, the Chen distribution of KS test has been employed. So for this data set, we observe the KS distance is 0.2027 and corresponding p-value is 0.5051. So this is the transform data, the step level x1, x2, the failure times this one, and table 5. In table 5, MLE and Bayesian estimate an interval estimate, an interval length for real data set. This is the estimate of alpha and MLEs and Bayes estimate. This is the confidence interval and average interval length, HPD class interval and interval length. This is the MCMC plot for the real data set. And we move to the conclusion. So from regarding the simulation table, we observe that the absolute bias and MSEs of the MLE of the unknown parameter decrease with the increase the sample size as well as increase the termination time tau 2 of the experiment. We can also observe that with a smaller value of n and higher m, the coverage percentage of asymptotic confidence interval estimate on known parameter are generally below of nominal level compared to HPT interval estimate, but the situation improve with putting higher number of experimental unit on the experiment and smaller percentage of censoring for both classical and Bayesian approach. It is also to be noticed that the average interval length and the asymptotic confidence interval estimate of unknown parameter also decrease, shows the improvement of coverage percentage with the increase the sample size termination time of the experiment. Next, we also note that the Bayesian estimate of the case of prior one having lesser absolute bias and MSE and average interval length with better coverage percentage compared to the Bayes estimate computed using prior one as well as MLEs using Nielsen-Raptor iterative method. In general, we can say that the increase in the value of n and m and tau 2 shows improvement in this result of estimate both classical and Bayesian in terms of absolute bias, MSE, and average interval length with coverage percentage. So these are my references. Thank you.
Thank you, sir, presenting your. I think it is a very genuine problem at once again.
Thank you, sir.
I hand over to the Satish sir.
Thank you, Professor. Thank you so much for the wonderful talks.
Thank you.
Professor, both we extend our gratitude thanks to both professors, Professor Harihar Linche and Professor Devendra Kumar for your wonderful talks. And also, we extend our gratitude to Professor Raghavendra Sharma for chairing the session. Thank you so much.
We are
Thank you.
very thankful for you, sir, for giving it a chance to make a chairing here. Thank you very
Thank you,
much.
Professor.
Namaskar.
Thank you. Thank you, sir.
Yeah. Bye.
Bye, sir.
Yeah. Now let us move to the next session because we have 2-3 minutes. Yeah, only. What about Professor Priyaranjan Dash? Professor Priyaranjan Dash joined.
Nadu. His main research work focuses on robust statistical inference. He has more than 20 years of teaching and research experience. He will be presenting on the topic Enhancing Model Resilience Robust Statistical Techniques in Machine Learning. Our second invited speaker is Professor Asha Gopalakrishnan from Cochin University of Science and Technology, Cochin, India. Her research interest includes distribution theory, reliability modeling, survival analysis. Her presentation is titled The Corrected Likelihood Approach for Adjusting Measurements Error in Cox Model. We are privileged to have both of them with us today. With that, I now invite our session chair, Professor Priya Ranjan Dash, to officially begin the proceeding. Over to you, sir.
Namaskar. Good evening to all. Now, I first.
Namaste. Namaste, bro. Namaste.
Namaskar. Thank you, the organizers, for uh, allowing me to join this session, chair this session. In this session, we have two speakers. Now, I request Professor R. Muthukrishnan from Bharatiya University to talk on the enhancing model resilience, robust statistical techniques in machine learning. Sir.
So I'm audible, sir?
Sir.
Audible.
Sir, good evening. Yes, sir.
Good evening.